Hi guys, I hope you all are doing well and staying safe. For the rest of the month, we're going to be talking about this next unit of waves. So let's get started. We're going to split these notes up into 3 sections. And like I said, by the end of the month, which is a couple weeks away, we'll have a test over waves. So what is a wave? A wave is a disturbance that carries energy through matter or space. So we already spent some time talking about what energy is, right? It's the ability to do work. I know that there's thermal energy, kinetic energy, potential energy. A wave is just a method that kind of carries energy through matter or through space. Most waves are caused by vibrating objects, and these are the types of waves that we're kind of most familiar with. So most people, when they think of a wave, they think of a wave like this, okay? A wave in the ocean or a body of water. It's not necessarily that the particles of water, they're moving a little bit because there's so much energy, but it's not like particles over here are going to end up all the way over here because of this singular wave. What's actually happening is that the energy is transferring to the next water molecule, to the next water molecule, to the next, and it creates a solution of motion. So something very similar that you guys might be aware of are dominoes. If I put energy into a domino, it's going to transfer that energy to the next one, to the next one, and so on and so forth. It's not that this domino ends up all the way over at the end, it's just transferring its energy to the next domino, or in our case, particle. We can see this here in a ripple of water. If you put energy here, all of these ripples are waves. They're showing the transfer of energy from water molecules over here all the way over here. Now, like I said, it's not like these water molecules are actually moving all the way over there. It's just transferring their energy. Another example is sound waves, right? Sound starts at an initial source, but how exactly do we hear it many feet away or even miles away? What's happening is that the waves are transferring their energy through the air molecules until it reaches our ear. So it's transferring their energy. It's not transferring this matter or space. It's transferring energy through it. As scientists like to do, they like to organize things. So we have 2 types of waves here. We have mechanical waves, which involve traveling through something. Whatever they're traveling through, we call this a medium. So examples are what we just talked about. We talked about water. The energy is transferring through the water molecules. Sound waves, that is transferring through the air. Even earthquakes. The waves we get are transferring through the earth, through the rock, and that's what generates an earthquake. So that's one type of wave. The other type of wave is called electromagnetic. So based off this word, I see the word electro, meaning electricity, right? And magnetic, meaning magnetic. So this involves electric and magnetic field in space. They do not involve a medium. Examples of this are light, X-rays, microwaves, radio waves, anything that does not require something to travel through, that's going to be electromagnetic wave. So water is mechanical, sound, mechanical. We'll talk about electromagnetic towards the end of this unit, but here's all my types of electromagnetic waves. So I have light, X-rays, microwaves, all of those things. So mechanical requires a medium, electromagnetic waves don't. Now that we know what a wave is, my 2 types of waves, let's talk about different parts of a wave. So we need to be familiar with all of these words right here. These are mostly just definitions, so the more you practice identifying what these words are, the more or easier time you'll have at remembering them. So our first 2 words are a crest and a trough. So I see here a picture of a wave. All right, this is the path that energy is taking, and it creates a wave like this. A crest is the top of the waves. So the very top of these waves are known as crests. The very bottom of these waves are known as troughs, right? What's a wave length? Well, based off the word alone, I would assume that it's the length of a wave. That's exactly what it is. It's the distance from any point on a wave to an identical point on the next one. So it could be from crest to crest, like I see here. This is a length, right? It's a space from one point on a wave to an identical point on the other wave. So this is an example of showing crest to crest. It can be from trough to trough, as I see here as well. Now, technically, it doesn't have to be crest to crest and trough to trough. It just has to be from one point to the next identical point. So if you look at my mouse here, if I started it here, a wavelength, this point is about to go up on the crest, right? So I would find the next identical point, which is right here, and it should be the same length. Amplitude. This is the distance from the starting point to the farthest point out. So we're going to usually see this line going across the middle of these waves. That's going to be known as our starting point. The distance from that starting point to the farthest point out, so from the starting point to the crest, or from the starting point to the trough, that's going to be known as the amplitude. Another term we have to be aware of is a period of a wave. Think of this as a period of time. So this is the time required for one complete vibration of a particle or one complete wave to pass. So this is one wave, right? One wave from one point to the next identical point. This is one wavelength. How long did that take for that to happen? Well, that's going to be the period of time it took. My next important term is a frequency. We use this word frequency in our normal everyday life. You should kind of relate this to terms of how fast or how much of it is there. A frequency of a wave is how fast these vibrations are occurring in the medium. So if this wave is traveling really, really fast, it's going to have a higher frequency. If it's not traveling as fast, it's not really passing as much, therefore it has a slower frequency. You might see this unit Hertz, this new one, this new unit we're going to use to describe frequency. There is an equation to figure out frequency. This year we're not going to spend too much time on this. Also, we should know that the higher the pitch, so this is talking about sound, okay? The higher pitch sound means that those waves are traveling at a faster frequency. So frequency is how fast it goes. Wavelength is the length of one wave. There's a very important relationship we need to be aware of for this. So this picture is on the last slide. Notice that this is a faster frequency. I can see that this wave is passing much faster and more frequent, right? Look at the wavelength here. Going from crest to crest, this is a short wavelength, right? But I have a big frequency, a fast frequency. Notice down here, if I have a slower frequency, I have a bigger wavelength. So looking at this picture, you should see that they're kind of opposite of each other. A small frequency equals a large wavelength. That's what's shown in this bottom picture right here. So small frequency or slower frequency means that my wavelength has to be bigger. A larger frequency, so shown up here, has a smaller wavelength. So notice, small, large, large, small, they're opposite of each other, and that's a very important relationship to remember. So we just learned all these words. Look at this wave right here. Look with your eyes, identify the crest of a wave. you should see something like this. This is a crest. Over here is another crest as well. Now identify the trough, which should be at the bottom of the wave. I also have another trough over here. The amplitude. Try to see if you can find the amplitude before I label it up here. The amplitude is going to be this distance from the starting point to the highest point. It could also be from the starting point to the lowest point right here. Notice that this distance and this distance should be the same. And then finally, a wavelength. Wavelength is going to be from one point on the wave to the next identical point on the wave. Okay? Easy way to do that is from crest to crest or from trough to trough, but keep in mind, it doesn't have to be crest to crest and trough to trough. It just has to be the next identical point. So looking at this picture, I see that this picture, I have two wavelengths here, right? And just for a review, frequency is how fast it goes, and a period is how long it takes for it to pass. All right, looking at this picture right here, which one has the higher frequency? This should be sound A. I could also ask you a question of which one has the larger wavelength. That would be sound B. If I was to look at my colors of light right here, I would say that the red one has a smaller frequency, but a bigger wavelength. The blue has a higher frequency, but a shorter wavelength. This one over here, notice if it's traveling at a higher frequency, the time period it takes for one wave to pass is shorter. Where if I have a lower frequency, the time it takes for one wave to pass is going to be longer. And this is just another visual to represent short wavelength means high frequency, long wavelength means low frequency. Last bit of information for this part one of their notes is we're going to talk about the Doppler effect. So when a source is moving, the observer notices a change in frequency. Remember, frequency is how fast it goes. So imagine there was just this source of sound and it wasn't moving. It would be traveling through the air in all directions at a pretty even rate, right? But imagine if the source of sound started moving forward. That means that it's going to start hitting those particles towards the direction it's moving at a faster rate. So look at my frequency here. It's starting to get faster going in the direction that it's moving. We hear this a lot when we hear sirens or vehicles. So have you ever noticed if you hear a fire truck or an ambulance, it seems to be getting louder, right? But it's not like they're turning up the volume of that truck. It just seems to be getting louder to us. Why is that? It's because it's moving towards us and the frequency is just higher at that moment in time. And do you ever kind of think that once it starts to go away, that it seems to get softer, right? But we know that it's not really getting softer. It's just that the frequencies are getting more spaced out. Therefore, it appears to be a lower pitch. There is an example that I will post with this video to kind of help you guys hear this visually, just to give you an example of it. So make sure you watch that. This will end it here for part one of these notes. If you have any questions over any of these words or what they mean, please feel free to email me.